Good morning, student. Today I will describe one more problem regarding the momentum balance. So in our previous class, previous few class, we have studied some examples of momentum balance. Means by which we can get the velocity profile, the mass flow rate, and the velocity profile in terms of the average velocity. And what are the problems we have done? We have done some flow of fluid over that inclined plate, and flow of fluid through a circular tube by gravity. Then some fluid will flow with the upward moving belt. Okay, so now today I will discuss a new problem, a new concept of the momentum balance. Okay, so today the discussion topic will be the laminar flow in a narrow slit. Okay, so the laminar flow in a narrow slit. So in this analysis, we are going to start the flow through a narrow slit. Slit means that the pressure gradient, gravity both present here. Okay, so in this narrow slit, their pressure gradient and gravity both are present, and slit is very narrow, such that the variation within this direction is important. Within this direction means the into the z direction, because the fluid is flowing from the top to from the bottom, from top to the bottom, means the velocity is in z direction. And another thing, the we are assuming it as a steady flow, one dimensional steady flow, so that there is no variation in the direction of flow. Okay, now here we can see that the two plates are situated at a distance of 2b apart. Okay, here the two plates are at a distance of 2b apart. Now the origin of the coordinate system is shown in this diagram, where the z direction is toward the flow. Now we have the flow from top to bottom, and the width of the uh, width of that narrow slit is w. The length of the two plate is l, capital L, and we can see that the Vz is the only non-zero component of velocity. Vz is the only non-zero component of velocity, and Vz is a function of x. Okay, Vz, velocity at z direction, is a function of x, not a function of z. Since it is a narrow slit, it depends of Vz on y. Okay, so as it is the narrow slit, it depends of Vz on y, which can be neglected. And what we mean means that the width is, if the width is too long compared to this gap, okay, means this means this width w is too long compared to this gap, through which that fluid is flowing. Means therefore what happens, near y equals to 0, or at y equals to w, that portion can be neglected. Okay, so at y equals to 0 and y equals to w, that portion we can neglect. So there are our assumptions that it will be the one dimensional flow and it will be the steady state. So we need to find out what is the expression of for shear stress to be used in this problem. So what is tau? We can see that the z momentum is being carried by viscosity in the x direction. Okay, means we can see that the z momentum is being carried by viscosity in the x direction. So therefore subscript tau should be tau xz, since the velocity varies with x. So our shell is going to the thickness, having thickness del x, the shell thickness will be del x, and x is the distance in which the dependent variable, the velocity in this case, keeps on changing. Means we are having the thickness of the shell is del x, and x is the direction in which the dependent variable, that velocity in this case, the dependent variable, keeps on changing. Now we are considering it as a Newtonian fluid which is flowing in a narrow slit formed by two parallel walls at a distance 2b and length L, width W, and also we are assuming it as a laminar flow and incompressible fluid which are having a constant density and also viscosity. Width of the slit is very small compared to the length and width of the plate. Okay, width of the slit is very small compared to the length and width of the plate, and the width of the plate, that is the uh, b means that the distance between these two narrow slit, b is less than w, that is the width, which is also less than capital L, the length of that two slit. Now consider that that this flow is in the z direction and there are no end effects. And now as there is a flow from the top to bottom uh, through these narrow slits, in between these narrow slits, so there will be two forces acting on it. One is surface force, which is the pressure force, and another is the body force, which is the gravity. And the P0, which is acting at z equals to 0, and PL is the pressure which is acting at z equals to L. Since it is a narrow slit, it depends of Vz. Since it is a narrow slit, so it depends of Vz, velocity at z direction, and the y is neglected. Okay, y, velocity at y direction, is neglected. So Vz is a function of x, not a function of z. Now we are making the following simplification, that is p naught small p naught plus rho g naught minus p small pl plus rho gl upon L, which is equals to p naught minus pl upon L. Here this p capital P naught is equals to small p naught plus rho g naught, and p capital PL is equals to small pl plus rho gl. So these are the simplification we are making so that we can get the velocity profile uh, easily. And the another molecular momentum flux which is given here, tau xz, tau xz. Okay, now we are having the narrow slit. Now we are assuming a shell in between this narrow slit so that we can make the balance over there. So the momentum balance at this shell, at this shell will be the rate of molecular momentum in across the surface at x minus a rate of molecular momentum out at the surface x plus del x plus external forces acting on the fluid is equals to 0. Okay, now we are explaining as a molecular momentum, not the convective momentum. Why we are not explaining that the convective momentum? Because the top and bottom shell convective mass are equal. So here, as the fluid is flowing from the top to bottom and the velocity is at z direction, it only as a it is a function of x, not a y. So if we make the convective momentum equation, so we can see that there the top and the bottom of that shell convective mass will be equal as the velocity will be equal. So it will the convective momentum term will be same for the top and the bottom. So the convective momentum term will cancel each other. So only the term will have that the conductive or the molecular momentum or the viscous or the momentum transfer due to viscosity. Okay, and the external forces which are acting on it. So the momentum balance equation at the shell will be the molecular momentum in across the surface at x, across the surface at x, and out at x plus del x. Okay, now if we are considering this shell, so at molecular momentum in at x, out at x plus del x, okay, and plus summation of forces acting on that control volume. Now the conductive or the molecular transport of momentum, what will be the conductive and the molecular transport of momentum here? It will be the area multiplied with the force per unit area. Okay, so area of this narrow slit will be capital L multiply with the W, the length with W means that width of that slit. So length multiply with the width, we can get the area of that narrow slit. If you multiply this area with the force per unit area, which is our tau xz, so we can get that conductive or the molecular transport of momentum. Now we are having this momentum in term and the out term. So in term will be at x and the out term the same term but at x plus del x. Okay, so here also the z tau xz, it determines the z direction of motion taking place, z direction of motion taking place because the velocity is at z direction vz, and the z momentum get transported in x direction. Z momentum get transported in x direction. Now the pressure force or the surface force and the body force which is acting on the control volume, that will be, as I have mentioned, that there will be a pressure at the top of that narrow slit which will be P0, and bottom of that narrow slit the pressure will be PL. So the pressure force acting on that shell over means it will be as this pressure force acting over that control volume. So on which area the pressure force is acting on W, the width of that control volume on the of the or the shell, that width W multiply with that del x, the thickness. So W into del x is the area on which the pressure force of the surface or the surface force is acting. So the pressure force will be W into del x multiply with P naught, which is in, minus out term W into del x multiplied with the PL, capital PL. So where this P naught and capital P naught and capital P capital L, I have mentioned that the capital P naught is equals to small p naught plus rho g0. Similarly for the PL, capital PL also, and there will be the another force which is the body force due to the gravity. So here the same things, the W means the body force, it is acting on that control volume. Okay, so the control volume, body force acting on the control volume, so it will be W into del x into L into rho. So the volume into density, it will be mass, and if you multiply with the means the g, it will act as a body force. So your body force term on the control volume, it will be W into del x into capital L into rho g. Okay, now as we have that narrow slit, and in between this narrow slit the flow is flowing in the z direction uh, towards the uh, towards the downward direction by gravity. So there will be some boundary conditions. So as we know that in the transport phenomena we are considering that two types of boundary condition. One is the no slip condition and another is no shear condition. So no slip condition prevail on the solid liquid interface, and the no shear condition, it is prevail on the liquid air interface. In so at x equals to b, when at x equals to b, the velocity at z direction will be 0. The velocity at x equals to b. Now what is b? B is this the distance between these two narrow slit. Now when x equals to b, the x equals to b means it is at the interface of that solid or the narrow slit wall. Okay, interface or the narrow slit wall means this surface, x equals to b. So x equals to b means it is at the solid and liquid interface. The solid is our narrow slit and the liquid which is flowing through these two narrow slit. So at x equals to p, the liquid is attached with this stationary slit. So here the velocity will be 0, because there is no relative velocity between this solid and liquid interface, between this narrow slit and the liquid interface. So at x equals to b, Vz equals to 0. Now at liquid air interface, when the liquid air interface will come, there always a shear stress will come, shear stress term will come. So at x equals to 0 means it is at x equals to 0, at x equals to 0 means at x equals to b means it is attached to the solid wall, but at x equals to 0 it is far away from that solid wall. Okay, means at x equals to 0 this tau xz will be 0, because this is the liquid air interface where the no shear conditions prevail, and the velocity going to be maximum at x equals to 0. Okay, means at x equals to 0 it means it is away from the narrow slit. Means whenever we are going away from the narrow slit, the velocity will increase, because both narrow slits are in stationary conditions, and whatever the liquid is flowing and whatever the liquid is attached with this narrow slit, it is on static conditions. So the velocity attached with that narrow slit, which is at x equals to b, the velocity is 0, and as we go further away from this narrow slit, the velocity will going to be maximum. Okay, so at x equals to 0 the shear stress will be 0. Now at steady state, we as we know that at steady state the governing equation, which is rate of momentum in minus rate of momentum out plus summation of all forces acting on it is equals to 0. So we have the convective and the conductive term also. So as I have mentioned that the convective mass in the top and the bottom of that narrow slit or the control volume is equal, the convective mass is equal, and the velocity at z direction is equals through this control volume. So this convective, as this convective mass are equal, so this convective momentum term will cancel each other. Only the term will prevail, that is the conductive momentum and the forces. So now here this is the LW tau xz at x, which is the conductive momentum in at x, minus the conductive momentum out, which is LW tau xz at x plus del x, minus the pressure force which is acting on that control volume in the top, which is W del X multiplied with the P naught minus W into del X PL, the pressure force acting on the bottom of that control volume, plus the gravity force, which is W del X L rho multiplied with G. Now these all is equals to 0 at steady state. Okay, now it will be 0 at steady state. Now after simplification and dividing by both sides by W L del X and taking the limit when del X tends to 0, so we get that limit del X tends to 0, which will be tau xz at X plus del X minus tau xz at X upon del X, which is equals to P naught minus PL upon L plus rho g. So which leads to the definition of first derivative, and from this differential equation we able to obtain the difference equation. We would able to obtain the to find that the differential equation. Okay, so it will be, after simplification, it will be ddx tau xz is equals to P naught minus PL upon capital L. So here this P naught and PL, these are the capital P naught and capital PL. Okay, so ddx tau xz capital P naught minus capital PL upon L, where this P naught is equals to small p0 minus rho g0 and capital PL is equals to small pl minus rho gl. Now after integrating of this equation, we can get that tau xz equals to P naught minus PL upon L into X plus C1. So we have one integral constant, which is C1. Now we have to find this integral constant by implying the appropriate boundary condition. Okay, so that we can get the C1. Now as here it is a shear stress term tau xz, so definitely here the only one boundary condition will come, which is the no shear boundary condition. Okay, no shear boundary condition, no shear will prevail at x equals to 0. Okay, at x equals to 0, where the velocity will going to be maximum. At x equals to 0, tau xz is equals to 0, because it is the no shear condition. So now after putting this value at x equals to 0, tau xz equals to 0, we can get the value C1, the integral constant, which is equals to 0. Now we have the equation after incorporating this C1. So we have that tau xz equals to P naught minus PL upon L into x1. Now for Newtonian fluid, as we know that the shear stress is equals to minus viscosity in the multiply with the velocity gradient. So minus mu equals to dvz dx, velocity as z direction upon dx. Now putting this tau xz in that equation, where the tau xz equals to P naught minus PL upon L x1. So it will be dvz dx equals to minus P naught minus PL upon mu L into x. Now again we need to integrate and separate the it means integration, integrate it by using that variable separation method. So where we can get that means Vz is equals to minus P naught minus PL upon 2 mu L x square plus C2. Now again we have another integral constant C2. Now again if you want to means find out that C2 value, so we need to imply a appropriate boundary condition so that we can get the exact C2 value. So at the means here the velocity is the velocity term is there, so there will be no slip condition at x equals to b, means when it is attached to the wall, the narrow slit. Okay, at x equals to b, the velocity will be 0, vz is equals to 0, so it is the no slip condition. So now after incorporating this boundary condition in that equation, it will be means we can get that C2 value, which is equals to C2 minus P naught minus PL upon 2 mu L into B square. Okay, now putting this C2 value in that velocity profile equation. So we can get that the Vz equals to P naught minus PL upon 2 mu L B square multiply with 1 minus x upon B square, x upon B whole square. So this is the velocity distribution of the flow in between two narrow slit, okay, so which is in parabolic in nature. Now we have to find the maximum velocity. As I have mentioned that the where the velocity will be maximum, when we go far away from the wall, okay, from as we go far away from at x equals to b, at when we go further means away from the narrow slit, okay, means at the center or the at x equals to 0, that the velocity will be maximum. So at x equals to 0, means if you put this x equals to 0 in that velocity distribution profile, so we can get the velocity at z direction, the maximum velocity at z direction, which is equals to minus p naught minus pl upon 2 mu l b square. Now we have to find out the average velocity. As we know that the average velocity is the volumetric flow rate upon area, okay, it is the ratio of the volumetric flow rate upon the area. Now what will the volumetric flow rate? Now again we have to double integrate that dx dy with that velocity. So first integral limit will be 0 to w, then second integral will be minus b to plus b, because these narrow slit are 2b apart, okay, 2b apart. So the integration limit will be, second integration limit will be minus b to b. So this double integration will be for vz at dx and dy upon the area. Area is 0 to w, and the second integration minus b to b dx dy. So after simplifying it, we can get this p naught minus pl upon 2 mu l b square integration minus b to b 1 minus s square upon b square dx. And again after simplifying it, we can get the average velocity is Vz is equals to p naught minus pl upon 3 mu l b square, okay. So we have the maximum velocity and we have the average velocity. From these two relation, we have that, means the velocity, average velocity at z direction, which is equals to 2/3 vz max, okay, because vz max is minus p naught minus pl upon 2 mu l b square, and the average velocity is p naught minus pl upon 3 mu l b square, okay. So the relation between this average velocity and the maximum velocity, it will be Vz average is upon Vz max, which will be equals to 2/3. Now the mass flow rate. How to find the mass flow rate? Again we need to integrate it, the 0 to w and from minus b to b. So for this case, along this velocity, we need to multiply with the density for the mass flow rate, okay. So velocity with the density, again dx with dx dy. So we get, after simplifying, the mass flow rate will be 2/3 w rho p naught minus pl multiply with the b cube upon mu l, okay. So we can we got the value for the maximum velocity, average velocity, and the mass flow rate, okay. Now this average the mass flow rate equation, with the mass flow rate, whatever we are getting, 2/3 w rho p naught minus pl b cube upon mu l, it is a very important relation which can be obtained from this analysis, that is a slit analog of this Hagen-Poiseuille equation, okay. It is very important relation which can be obtained from this analysis, that is the slit analog of the Hagen-Poiseuille equation, that is this equations, m dot equals to 2/3 p naught minus pl w rho b cube upon mu l. So this is the velocity profile when there is a flow in between the narrow slit. So here we can see that the velocity is at z direction, when it is in fully developed condition, there the velocity is this way, that the velocity at z direction, the velocity profile as z direction, which is a function of x, and the momentum flux distribution, which is tau xz, it will look like this. Okay, so this is the velocity profile and the momentum flux distribution for this problem. So thank you for this class. If you have further any query, you can mail me or the WhatsApp me, so that you can clear your doubts. Okay, so as we go through more many problems, we will be able very clearly how any numericals can be solved by using the governing equation, by implying the control volume, implying the appropriate boundary conditions. Okay, and for those we need to imply the appropriate assumptions to simplify the numericals. Okay, so thank you, students.